Hi, I'm Shannon Silopath.
And I'm Dennis Lakov.
And I'm Noah Tornell, and we would like to welcome you to the project demonstration for our multi-directional accelerometer.
Our project, like the name implies, is much like your average accelerometer. It reads the acceleration that the device has experienced and displays it on the OLED. Our personal aim for this accelerometer was to not only have it display the total magnitude of acceleration that the device has experienced, but to also display acceleration in the X, Y, and Z planar directions.
Of course, challenges came along the way. As we had little experience with the components and the libraries used for this project, we had to learn much from the ground up. This constant learning came with changes in design, and in the end we accomplished our goal by having an accurate, easy-to-use design with a readable OLED display.
We even have a 3D cube mode.
If we were to consider where we might take this project in the future, we could see implementation of wireless data transmission for testing vehicles and a button mode for switching systems for easier user interaction.
This is the accelerometer. On the front face, we have instructions on how to access different modes using the switches as well as the OLED display. For easier understanding, we also define access directions in reference to the face. On the side of the case are the switches. There is also an arrow indicating the Z-axis.
If we were to look under the case, we can see the inner workings of the accelerometer. While the design may look daunting to some, it is simply a few key components connected by a PCB. First, there are the switches with their wiring. These switches are connected to the microcontroller, which is connected to everything else. We have the accelerometer chip, the OLED display, the rechargeable battery, which is under the OLED, and the battery gauge chip.
Let's start with the very important accelerometer board. The IC we are using is the MPU6050. This board acts like a sensor for our device. We use it to record two things: temperature and acceleration. Temperature is seen in Celsius, while acceleration is seen in meters per second squared. The information recorded is pure data and will be sent to the microcontroller for processing.
The accelerometer uses a lithium polymer battery that has recharging capabilities. We didn't want the accelerometer to have a battery that needed to be replaced often, so we opted for a more long-term functionality. The rechargeable feature allows us to realize this. With this special battery, we needed a way to know when the accelerometer needed to be recharged. To do this, we have the microcontroller constantly check the level of the battery. The microcontroller will then send this information to the OLED for the user to read.
To create better quality of use, we decided to use an organic light-emitting diode display, or OLED display. The OLED display receives information from the microcontroller and displays it on the screen. This information includes the display mode, which mainly includes acceleration information, temperature, and battery charge.
Finally, we have the microcontroller. All other components connect to it. It not only assists with power distribution, but also processes data it receives from the switches, battery, and accelerometer chip. The data it receives and processes is then sent to the OLED. What is displayed depends on the mode enabled within the code.
The heart of our accelerometer's functionality lies in its sophisticated code, which orchestrates every step of the process. Here's how it unfolds. Upon system activation, we kick things off by initializing all essential variables and communication protocols. This initialization phase sets the stage for our display, battery gauge, and accelerometer, ensuring they're ready for action. Once the setup is complete, the system transitions into its main operational loop. Here, it first checks if the device has been powered down. Should the device be off, it enters a sleep mode, pausing all activities. This state conserves energy until an external signal awakens the system, readying it for action once more. If the device remains active, our focus shifts to gathering data from the accelerometer, specifically the MPU6050. To ensure the integrity of the data we collect, we employ calibration and filtering techniques. These steps are crucial for minimizing noise and enhancing the accuracy of our readings. Next, the system assesses the current settings, determining which modes are active based on the position of various switches. Depending on the selected mode, it performs specific calculations. These may include determining the magnitude of movements or applying quaternion-based mathematics for rotational analysis, particularly for applications like a 3D cube. An essential part of our routine involves monitoring the battery level. Should it drop below a predetermined threshold, the system shifts into a low power state. This mode conserves energy through measures like dimming the display and adjusting the MPU 6050's filtering settings, ensuring optimal power management. Finally, having completed these steps, the system cycles back to the beginning of the main loop, ready to repeat the process. This cyclical operation ensures that the device continually adapts to the user's needs while maintaining efficient power use.
Before we begin demonstrating the accelerometer, we will briefly explain how to access the modes. This table indicates how the switches need to be set to utilize the modes.
Magnitude mode is displayed when switches 1 and 2 are off. This mode displays the cumulative magnitude of all planes in real time. Imagine we have 3 acceleration vectors in all 3 planes. This mode takes a vector that is created in between them and displays its true magnitude.
The next mode is max magnitude. It is activated when switch 1 is off and switch 2 is on. The microcontroller records the highest magnitude value it experienced since it was turned on. This value is displayed for the max magnitude mode. Next we have axes magnitude mode. This mode is activated when switch 1 is on and switch 2 is off. It displays the acceleration experienced by all 3 individual axes at the same time. This is done in real time. Notice how the accelerometer is picking up the force of gravity in the z-plane.
Finally, we have something we're really proud of: cube mode. This mode is activated when both switches are turned on. This mode can be used to get an understanding of the accelerometer's current position relative to its upright orientation.
We were very happy with how our accelerometer turned out. Not only can it display the acceleration it experienced, but it can show highest recorded acceleration, individual accelerations, and a cube mode based on user input. We put great work to improve the user interface and included temperature and battery charge on the display. In an effort to accommodate for the long-term use, we implemented easy recharging for the accelerometer.
We hope users will use this to test other mobile devices or vehicles. If we wished to expand on this project, we could implement wireless connections so testers won't have to be in the vehicles that they create to try out this device.
Thank you for watching our presentation.